Hello, and welcome to the week 2 recap video. In this week, we talked about the notes on energy of atoms. We practiced some electron configuration questions, and we started on lesson 2, the periodic patterns in the periodic table. Let's see, we did not get to the notes on nomenclature and 3D structure. And looking at the agenda, let's post that up right there. Looking at the agenda for the week, let's see what was due. Looks like lesson 1 and the weekly reflection. Remember, every week you should be doing a reflection sometime in that weekend, Friday, Saturday, or Sunday. Lesson 1 should have been turned in along with your notebook. And so remember, just make sure you make a copy and send that email to me. And so let's get to talking about the evidence notebook. Last week we finished lesson 1. We finished the notes on subatomic particles, and we are now on the notes on the energy of the atom. And so we should see this image. And if you don't have that, what you should be doing is you should click on notes on energy of atoms, highlight the entire document, 4 pages, copy it, Control C, Command C, whatever you're using, and paste it into your notebook. That way, you don't need to send me multiple copies of the notes. You don't need to do anything like that. Just add on to the current evidence notebook. Now, looking at these 2 images, which we can actually just present here, it's the same image. But the overall idea here is that we're looking at something called the electromagnetic spectrum. What is the electromagnetic spectrum? It's basically the set of radiation that exists when electricity and magnets kind of just energized. As far as we're concerned, though, we're looking at these different types of waves. These are different types of EM waves. We're looking at radio waves, microwaves, infrared waves, visible spectrum, UV rays, X-rays, and gamma rays. Now, the idea here is that different chemicals, when lit up, when doing a flame test with them, like sodium, copper, and strontium, if you burn these elements, you get different colors. You get red for strontium, you get a little bit of orange for sodium, and you get like a greenish blue for copper. And so they produce different colors when energized, and the question is why? Why would they do such a thing? And if you were paying attention, the title of this section is called The Energy of Atoms. And so why do they produce different colors when energized? Because they produce different levels of energy. And so if we're looking at gamma rays and X-rays, gamma rays are over here, radio waves are over here. I said X-rays accidentally, I just meant radio waves. If we look at the difference between these two, if we're going from peak to peak, radio waves are really, really big. X-rays, however, or gamma rays, however, are very, very small. Gamma rays pack quite a punch. Remember from the last week's lesson, gamma rays go through pretty much everything. Concrete, lead, you would need several layers of lead, several layers of concrete in order to block off a gamma ray. Radio waves, however, are very slow moving. They're very not energetic. And so gamma rays, very short, X-rays are very long. Look at the difference here, 100 meters versus 0.001 nanometers. And so high energy waves are actually short. They have short wavelengths, whereas low energy waves have very high wavelengths, very big wavelengths. And so sodium, very low energy. It's not like an orange color. Copper, very high energy, 500 nanometers. Strontium, even lower than sodium. And so if we're asked the question, which has more energy, red light or blue light, the answer has got to be blue. The wavelength is much shorter, the energy therefore packs a bigger punch. Go there and clear that, and look at the notebook here, and there we have it. They produce different wavelengths and are energized differently. The gamma rays are energetic and faster, and the wavelength is very, very short, while the radio wave is essentially the opposite. They're slow, wavelengths are very long, and they're not very energetic. Now, to go to this image, let's scroll down here. If you take any element put it in a tube, right? The gas form of the element, you put it in a tube and you run some electricity through it, that element should get energized. And when it gets energized, it produces a very unique color. Every element produces its own unique color. And if you take an instrument called a spectroscope, you could see its emission spectrum. And so what's happening here is that you have an element. Let's say you have hydrogen, right? Hydrogen, let's draw better. Hydrogen is one proton. It's got a positive charge to it because it's a proton. Hydrogen is one electron because they balance out those charges. And so normally the electron is pretty close to the proton, right? It likes being close. It's a negative charge, it's being close to a positive charge. It likes doing that. This is its ground state, the normal area, like normal state. But let's say you throw some electricity into it. That electricity gets absorbed by the atom, specifically by the electron. Now that electron gets excited. It's like, oh my gosh, I have so much energy, and it shoots up, right? It shoots up and it kind of stays there for a bit, but eventually it misses home. It misses that proton, misses that positive charge, and it eventually will come right back down to where it is. But when it does that, when it comes back down from being excited, right? It's like a sugar rush that you crashed from. When it comes back down, the energy that was inside of it leaves, but this time it's colored. And so you'll see different lights, different colors, right? Light blue, red, green, orange. You'll see all those different colors when that electron jumps back down. And so for hydrogen, you get 4 different bands specifically. You get a band at 410 nanometers, 434, 46, 656. And every element has its own unique band. If you look at lithium, it's got green, red, a little bit darker red. That's about it. If you look at the calcium, it's got all these different bands out here. If you look at just barium, it's got 1, maybe 2, 3, a few out here. And so you see different levels, different colors based on each element, and it's different emission spectrums. You could identify an element based purely on its emission spectrum. And this is actually how astronomers find unique elements out there in space. They look at the light, they divide the light into these spectrums, and they're like, oh, okay, this has got a lot of hydrogen out here. That's how we identify stuff in our space. And so the question I was asking to you guys is, how do you know which is the most energetic band here? And we're picking 410. There are 2 ways to know that 410 is the most energetic wavelength there. And one is to, well, first of all, know that 410 is closest to 400. Because if we're talking about high energy, the smaller number you are, the higher the amount of energy you have. And so blue, next to 410, very high energy. The other way to know is based purely on color. If you guys remember that phrase, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So if it's closer to violet, it's probably very high energy. Right, then followed by blue, light blue, orange. And so 410 has the highest energy because it's the shortest wavelength, meaning it's going to hit more and more frequently. All right. Now we come to the part where I find most people will struggle with. It's electron configuration. Now, one of the questions, one of the things we had to do for vocab was this word called orbital. And this is where electron configuration comes in. An orbital is basically where an electron can be found. There are several different types of orbits, S, P, D, and F, and they describe the shape of that orbit, but that's not too important right now. Just know that there are different types of orbits. And so an electron will travel in these orbits. And let's go through and talk about electron configuration. This is actually pretty good. And so for electron configuration, there are a couple things we want to know. We want to set it up in this pattern. The energy level first, the type of orbit second, and the number of electrons in that orbit third. And so let's pick a random element. Let's pick, I don't know, we'll pick red here. Draw it out, and let's just pick, yeah, this one. I think that's arsenic. I'm not too sure. And so we want the electron configuration for arsenic. To figure that out, by the way, electron configuration is just how these electrons are organized. And so arsenic, being element number 33, has got 33 electrons. We want to figure out how those electrons are organized. And so electron configuration lets us do that. So the first 2 electrons are in the first energy level. So this is 1. And in that energy level, the type of orbit that exists is only S. Next up, in that orbit, we only have 2 electrons. And so in the first energy level, there is only the S orbital, and there are 2 electrons in there, 1 S2. Next up, in the second energy level, we have 2 different types of orbits. In that S orbit, we have 2s. There are 2 electrons in the S orbit, 2s2. In the P orbit, this is 2p, there are 6 electrons, 2p6. So in this second energy level, we have a total of 8 electrons. Hopefully that's readable. I'll write that out a little bit better. Total of 8 electrons, 2 plus 6. In the third energy level, we've got the same deal. In that first orbit, that S orbit, there's only 2 electrons, so it's 3s2. And then in the P orbit, there's still 6 electrons, so it's 3p6. And now we're down to energy level number 4. So where things will kind of get complex, which just follow along. In the fourth energy level, in the S orbit, we still have only 2 electrons. So we'll just go ahead and write that guy out. 4s2. If I could fit this all in one line, I would, but I can't. Next up, we got the D orbital. Finally reach that guy, but it's just 3. 3d. And it's got 10 electrons in it. So 3d10. And then finally, we have reached arsenic, the level with arsenic in it. So it says 4, still the 4th energy level, but it's the P orbit, and arsenic is the 3rd element there. So it's 4 P. And so that's how we do in electron configuration. We go through every single electron in on the way to our target. Our target here was arsenic, and so it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Next, I talked about a shortcut method, and to do the shortcut, you just look at the last time the previous energy level was complete. So we're looking at 3p6, so you take argon and you put it in brackets. And so as a shortcut, you put argon, put it in brackets, and then you just go on from there, right after 3p6. So it's 4s2, Whereas 2, 3d10. Hopefully that looks like a 10. And then 4p3. Now the reason we talk about electron configuration, it's 2 real reasons. One, electron configuration lets us know what elements will react with what other elements. And more importantly, at least as far as I'm concerned, it lets us figure out the valence electrons of a given element. And so if we are talking about arsenic, it's actually it's actually AS. So if we're talking about arsenic, we're talking about the valence electrons in arsenic. What we do is we find the highest energy level in the electron configuration, which is 4. So every orbital that has the fourth energy level, so in this case, there's only 2, we add up those electrons. So in the case of arsenic, it's got 2 electrons in the s orbit, 3 electrons in the p orbit. So arsenic, As, has 5 valence electrons. I symbolize that electron with a negative sign just to remind us that electrons are negative. And so this is the reason why I talk about, electron configuration. It is complex, don't get me wrong. And I'll talk about this more on week 3 and as we go on. And so there are several examples here. Here's a potassium, for example, 1s2, right? Well, for potassium, it's in the 4th energy level, so we got to go through the 1st, 2nd, 3rd, and then the 4th energy level. And so we do that, 1s2, 2s2, 2p6, 3s2, 3p6, and potassium is the first element in that 4th energy level, so it's the s orbit, and it's the first one there, so 4s1. Okay. So I went through and did a few examples. You got argon and calcium here. Argon is in the 3rd energy level. It's the last one there, so you'll find that it is 3s2, 3p6. Right? We put neon in brackets because that's the last element that had a complete set, if you will. Whoa, 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 whoa. Too much. There. And then we had calcium, which is just 1 above potassium. So this is 4s2. All right, so as we go on, just make sure to use this chart to get familiar with electron configuration. And I'll show you some shortcuts later on. Now, I talked about figuring out valence electrons using electron configuration. As you know, as you should know, pretty much every element has an equal number of electrons. So if I have 40 as my element number, I've got 40 electrons. If I've got 82 as my element number, I've got 82 electrons. But for the purposes of reactions, it's the valence number that matters, the level on the outside layer. So we see that in this image here. Actually, let's go through and make sure we have the definition down. Valence electrons are those outermost layers, and most elements want to have 0 or 8 valence electrons. They want to make sure their valence shell is filled, right? It's like having a void that you got to fill with chocolate. They want to have 8 valence electrons. So for example, lithium only has 1 valence electron. It wants to get rid of its last electron in order to rejoin. Like it wants to lithium wants to get rid of its electron in order to become stable like helium was. And so we have to show how we write valence electrons down. And so let's take sodium. Sodium has 2 electrons in its inner layer, 2 plus 6 electrons in its middle layer, so a total of 8 electrons there, and then only 1 electron in its outermost energy level. And so the way we draw this in like on paper would normally be sodium, the symbol for sodium, Na, with just a dot on the side. That's it. And this tells us that there's only 1 valence electron for sodium. And so going back to the previous questions, argon has a total of 2 plus 6, 8 electrons, and calcium in its 4th energy level only has 2 electrons. So when we draw them out, argon should have 8 dots around it, and calcium should just have 2. If you don't know how to draw it in, a statement will be just fine. On P-Table, that website, if you ever struggle to find the electron for anything, it is the last number off to the side here. So tin, for example, will have 4 valence electrons, 2 electrons on its inner shell, 8 following that shell, 18, then 18. So we've passed 1, 2, 3, 4 energy levels. We're on the 5th energy level. And if we look at our period here, yeah, we're on the 5th period. Fun stuff. Last but not least, we want to remember those neutrons. And so this brings us to this thing called AZX notation. $10 to someone who figures out why it's called AZX notation. This notation lets us figure out a couple things. It lets us put mass and atomic number on paper, so it puts that in our vision, and it has a symbol for whatever chemical we're looking at. Now, the mass number might vary sometimes, and this is why this notation is useful. Atomic number will never vary, right? We know what an element is based only on its atomic number. So if I have 34, that's my atomic number, that's my number of protons. And that gives us the identity of this element. If I take element number 42, molybdenum, don't know how to say that. If you take element number 42, it has 42 protons, its atomic number is 42. But the mass, the total mass might change. And so if you look at things like uranium or neptunium or plutonium, you'll see that they have parentheses around them. And so the mass of this element is 244, but it's in parentheses. It's in parentheses because we are not sure about the natural abundance. And so plutonium only exists in several different isotopes. Think of isotopes like a twin with like different colored hair. They're the same element, but something's off, right? Isotopes of different atoms, different elements, have different numbers of neutrons. The protons and the electrons are the same, but the neutrons are different, which makes the overall mass different. And so we have uranium. Uranium is element 92, and you'll see that in both places here. 92 and 92. Uranium's mass is normally 238. However, with some refining, you can get that down to uranium 235. Now, to figure out the number of neutrons, all you typically do is subtract these two numbers. And so normally, uranium has 146 neutrons, but an isotope of uranium could have 143 neutrons. And that can make all the difference. Uranium 235 is, I believe, refined uranium, and that's the stuff you find in nuclear weapons. And so that's a pretty big difference. And so what I have you guys do is calculate the number of neutrons, protons, and electrons in argon and calcium. As you can see, for protons, that's just the atomic number. Element number 18 for argon, element number 20 for calcium. Electrons always match the protons, so 1818, 2020, easy peasy. For the atomic mass, I have you guys round up, I think. No, round down. I think in this case, I just have you guys round, whichever is closest. And so they're both 40 in this case. So the atomic mass for both these guys is 40, and you just subtract the number of protons to get the number of neutrons. So argon will have 22 neutrons, calcium will have 20. And that brings us to practice. Now, for the practice that you have to do, which is due by Friday, January 29th, you have to identify, or you have to put the elements in the following order from highest to lowest. And so you're given the colors that these elements burn, and in order to do this question, you just have to look at the visible spectrum. This one right here, right? Which is high energy, which is low energy. Next up, we want the electron configurations for aluminum, silicon, carbon, and sulfur. I've worked with you guys to do aluminum. Up to you to find silicon, carbon, and sulfur. Next up, state the dot structures for aluminum, silicon, carbon, and sulfur. We're working with the same elements every time here. If you, again, can't draw it up, a simple statement will do. And so for aluminum, we look at the highest energy level in aluminum. In this case, it was 3. We add up the electrons in those orbits, so 2 plus 1. And so aluminum has 3 valence electrons. And then we place what we put, what we figured out into this chart here. The atomic number for aluminum is element number 13. The mass of aluminum, in this case, I asked you to round yourself down, is 26. Figure out the number of neutrons, which is just the subtraction here, 26 minus 13. The number of electrons, which will always equal the atomic number, and then the valence electron. Straightforward enough, just some practice. It is what it says on the label. Practice. All right, now this brings us to patterns in the periodic table. And so like before, you should have opened up lesson number 2, periodic table. Click on that dot, copy and paste the entire document. Don't make a copy, just highlight the entire thing. Like 8 pages, I think. Highlight the entire thing, Control C, and then paste it in. And so we're looking at numbers 8, 9, and 10. This assignment is probably going to be the longest assignment for this unit because it is such an important thing to recognize these patterns in the table. It's something I'll refer back to very frequently. And so we have to understand what the periodic table is. So it is a period on the periodic table. It's just a horizontal row from left to right. What is a periodic law? Well, it's the idea that chemical properties tend to repeat along a period. So if we're looking at energy levels, for example, you'll see that, oh, it gets dark green and then it has to reset over to light green. If we look at ionization, we'll see a pattern again. So it get darker as we go towards the right. And so periodic law is really just that. It's the idea that these properties will repeat periodically. What is a group? Also called a family. And so a group on the periodic table is just a vertical column. To specify here, a group is also sometimes called a main group. And so main groups are groups 1, 2, skip a few, go all the way down to 13. So these are your main groups here. 1, 2, skip all the way down to boron, carbon, nitrogen, oxygen, fluorine. Those are your main groups, also group 18. These transition metal groups are still groups, but they're not exactly main. Now, how is the table organized? Atomic mass or atomic number? We've discussed this. They are organized by atomic number. They are organized by atomic mass. You could say that you should say then that argon and potassium are 39.09, argon with 39.94. They should switch places if we were organizing this by atomic mass, but we don't. It's only atomic number. Okay. Now, for the more extensive part of this assignment, I had you guys create your own periodic table. Obviously, I'm aware that p-table and other sites like it exist. There's a huge amount of information on the internet, but it does you no good if you don't understand what you're looking at. And so I have you make your own copy of a blank periodic table. And once you do that, you should insert that copy as a link up to number 4 here. And so originally this image was blank. It was literally just maybe the metalloids highlighted out, and that was it. As time goes on, you're going to be editing this image to include these trends, include the groups. And so I'm not trying to teach you the individual elements. That is not the point of this table. The point of this table is to look at an element and be able to figure out a few properties of that element. And so if I ever point out alkali metals, you should already be thinking, okay, that's one of these elements off to the left here. If I'm talking about my noble gases, you should be thinking about, oh, it's helium or krypton. It's one of those gases. That's what we're doing here. I'm making you guys memorize the individual groups, which is, there's not many. There's 1, 2, 3, 4, 5, 6, 7. There's 7 total groups. It's not a lot to ask. I know back in my dad's day, they had him memorize every single element on this table. Every time he tells me that story, I'm just forced to not say why. And so what you're doing is you made your own copy. You want to link that copy in, so make sure you go to share. Where it says copy link, you want to press that in. And then paste it right here where it says paste a link to your copy of the table. Or you could just go to insert and insert link. And you could insert your own link right there. Either one. Now, I have you guys list out the valence electrons. We did that in class. Basically, what you're doing here is you're pressing onto the thing, pressing edit, and you're just typing it in, right? 1 valence electron for everything in this group. 2 valence electrons for everything in this group. Skip a few, 3 valence electrons, so on and so forth, all the way up to 8. I had you guys create labels and a color key for the alkali metals, alkali earth metals, transition metals, post-transition metals, non-metals, halogens, and noble gases. There will be some overlap between the non-metals and the halogens, but that's the only place there will be overlap. And so looking at our table, we can kind of make a few immediate assumptions. Where are the metals typically found? If you look at our table, the metals, right? Sodium's a metal, magnesium's a metal, gold is a metal. The metals are all found on the left-hand side. Here. Metals are all found on the left-hand side, and therefore non-metals are on the right. You have to do number 7 on your own. Metals, what are the properties of metal? Ah, my gosh, properties of metals, metal as a non-metal, so you have to do that on your own. And so we will go over to ionization. And so this is a kind of complete looking characteristics of the periodic table. We're specifically talking about ionization energy right now. For ionization energy, that is just the energy needed to take an electron. And so if I have like a 3-year-old and a fully grown adult, and they both have candy bars in their hand, the 3-year-old has a very low ionization energy. It does not take that much force to steal candy from a 3-year-old. But the fully grown man, he's going to want his candy. It takes a lot of energy to get the candy from him. And so if we look at these numbers here, helium has got a very high ionization energy. It takes a lot of effort to remove electrons from helium. Look at cesium over here with 376, very low effort, super easy to get rid of an electron here. And so the pattern is that ionization energy increases in this direction. So the closer you are to helium, the harder it is for you to take an electron from these elements. And the closer you are to like cesium, the easier it is to take an electron. Something I want to point out about ions, by the way, is how they're written out. And I'll talk about this multiple times. Let's take hydrogen. Hydrogen's chilling. It's a single proton. And it's got a single electron. Let's say oxygen comes in with its extreme positivity and just kind of takes the electron. What happens is that hydrogen has become an ion, and so it is positively charged. It loses an electron, and to most people, they'll think, oh, okay, that means it's got a negative charge, so it lost an electron. But no, we're talking about charges only. And so hydrogen by itself doesn't have any kind of plus or minus attached to it. But if it loses an electron, it gains a positive charge, +1. Oxygen normally is just like this, but if it gains an electron, it's a -1 charge because it gained a negative charge. So that will get confusing. I understand that, and we'll have more practice as time goes on. But this video is running a bit long, so I want to wrap it up. Now, ionization energy repeats across a period, and so you'll notice that as you go farther and farther out, that period gets higher and higher as far as ionization energy goes. And so, why do noble gases have high ionization energy? It refers back to the valence electrons. If you look at this number, the noble gases have 8. They're done. They do not want to get rid of their electrons. It's like a noble with its wealth. The valence electrons are the wealth. They are not giving up the wealth. And so they have high ionization energy because they're very, very stable. Why would magnesium react with hydrochloric acid more than aluminum? Even though aluminum has higher or lower ionization energy, magnesium has less valence electrons, so it refers back to valence electrons. What I'm trying to point out here is this idea that it's a combination of these factors. Ionization energy plays a role, but so does the valence number. So does the atomic radius, which we're going to talk about right now. And this will be the last one because most of my classes didn't get to electronegativity. So atomic radius is what it says on the tin, the size of an atom. And so if we're looking at atomic radius, oops, there it is, you'll notice it's the opposite of ionization. If I look at cesium, it's a huge atom. And if I look at helium, it's so tiny. And so one of these things is these ideas are related, ionization and atomic radius. It's like, and here comes the metaphors again, it's like a guy with 3,000 bags of chips. He's not going to really notice if you come in and take another bag of chips. Go for it. But helium is kind of like a starving kid. It's going to want that bag of chip the most, it's going to really, really want that bag of chips. Because the size is so condensed, it's going to really hold on to it. So atomic radius is the opposite pattern of ionization energy. And so within a period, the atomic number, the larger your atomic number typically, or the smaller your atomic number typically within a period, the larger your size is going to be. So you look at 37 versus 54. 37 is massive. As you go down the group, it gets bigger and bigger and bigger. And it has to do with the fact that you're adding more and more protons, more and more electrons, right? You're adding 82 protons and electrons to lead. That's a lot of space it has to cover. And since it's 82 protons, it's very positively charged, so kind of hold on to it, really condensed. Cesium, though, is very loose. It's a very loose formation. All right, so in the next video, we'll go through and talk about electronegativity, which is where we're starting off next week. Period 7 about ended here, period 1 ended around here. So the rest will be covered next week in the week 3 recap. Hopefully we enjoyed this lesson. I'll make sure to put, what do you call them, timestamps for the different parts of the week 2 recap. But until then, I hope you enjoyed this video. Don't forget to like, comment, and subscribe. This video has been brought to you by Raid Shadow Legends and let's say Monster. Monster Energy is now sponsoring me. They're not. All right. Have a great rest of your day, everybody. Bye-bye.